Oh, that's not.
Okay, guys, let's go and get started.
Okay.
Today, hopefully, will be super short, despite the number of slides you see. But we're going to go over Chapter 1.
Whoa.
Okay? I've saved Chapter 1 till now.
Oh, God.
So hopefully, we can all figure out what's going on and pass the Chapter 1 homework. Get my marker.
Did you expect enthusiastic applause for that?
Look, I've really had a lot of trouble with this homework, and I don't really know why. I haven't figured out why everyone messes this up. But we're going to go over Chapter 1, which has to deal with performance, aka gauging how quickly something can accomplish a task, and gauging how much power it consumes. So there are different performance metrics, and we're going to discuss each one of them. But since this is Chapter 1, we're actually going to go back and do a full overview of how everything works. This hopefully is a good review, but if something is confusing, make sure you stop me so I can explain it.
They look more like your slides now.
Right, I just took his slides and put them inside of Maya with the tech slides, so hopefully they will work better. But we'll find out.
Got the little progress part at the top.
Yeah.
Yeah, it lets us know how far we have.
Yes. All right, so your program. It's best to think about, well, one way to think about it is like an onion, with layers. Outside you have your application, which usually runs on top of system software, which is usually just a bunch of libraries. And then below that, before the system software, there's the kernel, which then interacts with the hardware. So keep in mind that when you run your program, you're using a lot of library code, which is then translates what you want into actual hardware commands. Hardware has a processor, memory, and I/O controllers. All right. Anyone confused yet? Okay. Levels of code. Hopefully this is very familiar. You have your C code, which goes through a compiler and generates assembly. Again, a compiler does not generate machine code. All it does is translate your high-level language, like C, to assembly. And then your assembler and, well, your linker will change it to a binary representation. Good? All right. Whew. So the CPU has data paths, which performs operations on data, like add, multiply, load, store, move things around. And then we have cache memory. Do you all know what a cache is? Are you sure, Jonah?
Yeah.
Oh, yeah?
That's
Good.
what SRAM.
Hey, look, the Apple A8. This is kind of old. That's all right.
Is that what you want us to draw for architecture?
Yeah, draw this, and I will laugh. And then put a 0.
Okay.
Nice.
I mean, it's better than drawing a house.
Well, no, the house got 1 point, because that was at least clever.
So
Where do you
want
store
that
your
to be
data?
right.
All right, I don't know if we talked about this. So there's volatile memory and non-volatile memory. Volatile just means whether or not it gets erased when you turn the machine off. So something that's non-volatile is your magnetic disk, because when you turn your machine off, it's still stored there, right?
Yeah.
Same thing with flash and your optical disks, aka CD-ROM, DVD, and Blu-ray.
Those things.
Yeah, those things. All right, and what would be an example of volatile memory?
RAM.
Okay, good. Anyone confused yet? All right, we're doing great. So there's these things called networks. Have you all heard of these?
Sure.
Yeah.
Wait,
what?
What is this?
It's a myth.
It's a myth. All right.
The
They
myth.
use to
The
communicate
legend.
between machines. You have local area network. We usually use Ethernet, although there are others, like InfiniBand. Wide area, usually referred to as the internet, but you usually have some other type of architecture running around. You have wireless, aka Wi-Fi and Bluetooth. All right.
Yeah.
Technology has increased exponentially.
Yeah.
If you look at this graph, this is linear progress of time, and this is a logarithmic scale of density of transistors. Oh, this is going to be cost per performance. So if you say that the vacuum tube, which you all have one at home, right?
Yes.
Oh yeah.
When the when the
sucks.
You all know.
Nice.
You should be very disappointed.
Wow. No, I am not. I liked it. Because when the EMP blast knocks everything out, at least your vacuum tubes will be working. I don't know what you'll use them for, but whatever.
At least they work.
At least they work. Yeah. Anyways, we say that they have a performance cost of 1, and higher is better. So transistors 35 times. The first IC integrated circuit, which we created with Verilog.
Okay.
And then basically all these next ICs are just smaller and smaller, so you can put more transistors on the chip.
Whoa.
Whoa. And by increasing the capacity or the number of transistors you can put in an area, it usually increases your performance because that's less distance the flow of electricity has to travel. And also, in general, we've been reducing cost as well because you need fewer materials.
Yeah, squish them all in there.
Squish them all on there. Just stuff them in there, right? Yeah, that's how it works. We just keep stuffing.
Yeah.
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 Any questions yet? Man, we're doing okay. All right. All right, we talked about silicon, which is semiconductor, and you add things to it to make it a conductor, an insulator, or a switch. Great. Hey, look, here's the process. I think I've showed this before, right?
Yeah.
Good.
Been there,
Done that. Look, here's a picture of what it looks like.
Whoa.
All right. Whoa. Okay. Hold on.
Whoa.
All right. This is where I start losing people. Right here.
Dice per wafer.
So,
I was lost on overview.
Why are we
overview.
dying?
So again, just to recap, you have your silicon ingot, which is a cylinder. It's hard to show a cylinder in 2D, but it's a cylinder. You slice it up into wafers. Then you do some magic. That's what this box is. And it has patterns on the wafers. You can test the different wafers, see if different wafers fail. And then you can dice them up into chips, test the dies, see if they failed, bond them to a package, test the package to see if these failed, and then go ahead and ship them to customers. So the point here is the point here is that there's a lot of points. The point here is there's a lot of, I guess, steps in the process that things can fail. All right? And if 90% of your stuff fails, that's bad, right?
What?
Yes, because
What?
I mean, you still got 10% that works.
Yeah.
That's still an F though.
but it is an A on failure.
Yes.
That is true.
Ah, see, you just gotta
I
gotta spin it the right
fail
way.
plus.
Yeah,
I got a fail plus.
you just gotta spin it the right way, Sydney. Okay?
You got an FA.
Yeah, no, that's something else. That's failure due to absence. You gotta
Is
get
it
your
an AF then?
No.
An A in failure.
No,
So
no.
AF.
No, A in fail. Okay, sure. That'd be an AIF. You have to have
I
TLAs.
have little.
That means
TLAs.
That means the AI fails.
Yeah.
All right.
Exactly.
So we want to know
Dies.
how much each die costs because that'll tell us how much to charge our customer. So first you need the cost per wafer. Remember that's that big circle. And you want to divide it. So if this thing is $50. Actually, that's usually a lie. We'll say 500. It's much better.
Whoa.
Huh, there we go. Very
How many
nice.
dies do you get per the wafer? We'll say
That depends.
122. And then the yield, aka how many of those happen? Well, 90% failed, then be 0.10.
That's not very good.
And that's how much it would cost on average to produce a die. Anyone confused?
Wait, what did you just say? You said dies?
See, every time.
No. On the bottom, dies per wafer times yield. So you're saying only 10% of the wafers pass?
Yes.
Yes.
If we were saying 90% failed.
You got it.
It's $500 per wafer.
Sure, why not?
Vanilla wafers or?
That's 40.
Look at that.
Those vanilla
40,
wafers better sing to me while I
per
eat
die.
it.
They're coated
Isn't
in
that
gold.
really funny?
They have everything you need for a whole week.
They're coated in
survive.
gold.
500 for wafer.
But then you only have to eat once per week.
That's
Oh,
not
that's
fun.
not fun. I
Yeah.
like food.
The process of
I'd probably take that. I don't like eating.
Cost per die.
Well,
Is that what?
well, you also sit there and eat broccoli all the time by itself.
Like I said, I don't like eating.
Broccoli's
Not
good.
with cheese. Broccoli's good, but like with cheese or some A1 sauce.
Any questions
you know,
about the cost per die?
shake it
You
up a
don't
little.
like eating?
No, I do not like eating. Eating and sleeping, I don't like doing.
What?
Why?
No, I got it.
Because he eats broccoli. If he ate something decent, he'd
Yeah, that's true. You gotta get.
I mean, I've had other stuff.
Like what kind
Mix
of?
that with some broccoli and cauliflower.
You just think of it as waste of time because you're like, I got other stuff to do.
Yeah, there's other things I'd rather do than eat and sleep.
Oh yeah.
See,
I
but
don't
if you
know. Eating and
multitask.
sleeping is pretty awesome.
No, when I was a
I just
kid.
do it because I have to.
All right.
Any questions on cost per die?
Robot.
No.
That depends on your definition of robot.
Oh wait, no, I actually want to know more
Stop.
about this.
Cut.
We want to get out early.
Dies per wafer. So if you notice in this top formula, we have to figure out how many dies could be in
Yeah.
the wafer, right?
So we gotta figure out that.
Well, you have the wafer area divided by the die area. Is that going to be the exact number of dies?
No.
No,
No, why is that?
because there's some on the edge that are cut.
Yeah, see how some of them have been cut off?
That
All
would
right.
bother me so much. It's so much wasted space. Like, why don't you make it squares then? Or rectangles?
Because
Cut
then
it.
your manufacturing would have to use cube.
Pipes.
Yeah, that would not work out well.
Yeah, but
Cube pipes
Would
are hard.
not. Yeah, they don't roll very well.
Oh yeah, you'd have to transfer them differently.
All right, so everyone okay with dies per wafer?
Yes.
All right. And then what is your yield? Oh boy, this is where everyone goes crazy. Okay. Morning. Anyone know this formula? Look. So, what's defect per area?
the number of ones that don't work in the area.
Okay, the number of defects in the area. Okay,
Mhm.
great. And then the die area?
This is
How much
On his
area
face,
the
the
die takes
die
up,
takes
yeah.
up.
Yeah.
Okay.
Divide that
Yeah.
by 2.
Yeah, why are we dividing it by 2? You don't know?
Because.
Because there's stuff that doesn't work.
Yeah.
Let's put some numbers in there just for fun.
I like
Well,
What would the
numbers.
die area be? 50?
Sure.
Sure.
50 millimeters squared.
Well,
Well, I'm sorry, the defect per die area. Whew, that was bad.
You forgot the plus sign after the one.
How many defects should we have on average per die area?
Well.
A lot. So if you're gonna say that it's like 10, if it's
Is
a
it
10%
90%?
success rate, so there's gonna be a lot of defects per area.
Okay, so 0.9
yeah.
times the die area, which is 50 millimeters,
Divide by 2.
divided by 2.
So defect per area is a percentage.
Squared.
Oh, we gotta square this.
Yeah, we
Yeah,
also
it's
forgot the
like
plus
the whole
sign.
thing.
Oh,
You spread the whole thing.
So what's 0.9 times 50?
This is just completely ignoring us.
I am totally completely ignoring it. 54, 1
That's
point.
rude.
I do that.
Wait,
Square.
wait.
you never divided by 2.
You divide by 2.
Man, y'all are such complainers.
Wait.
Complainers?
Wait.
0.9
So
times
25
25.
times 25.
It's 22.5. Where did you get the point?
I'm just gonna do
Oh, you already added the one.
Yeah. Squared. Squared.
And then 1 divided by that, what does that get you?
The yield.
Why?
Good answer. Hold on. 1 divided by.
Yes.
Why is 0.9 times 50 0.225 and why isn't it 22.5?
Because I couldn't do math today.
Okay.
So in an ideal world, yield would be 1.
So it should be 23.
Yeah.
It should be 23.5 in there.
20 what?
3.5.
Okay, now you gotta square it.
Yeah.
What does that give you?
Ah.
1 over.
23.5.
What's 23.5 squared?
552.25.
0.0018.
Yeah.
Which is what?
0.0018.
Right, so your yield is
Pretty
not
good.
even, it's
That's
0.18%.
Terrible yield.
Yeah.
Taking the pictures.
Taking the pictures?
Let's
Take
Yeah,
a-
because
take
we don't
a
ever
dump
record
picture.
Good to go. We don't need to improve our process. There's nothing wrong with it.
Absolutely
Now,
nothing.
This yield, the yield to the square, right? Your yield is like an error formula or?
Yeah, it's an error. The point here is, notice it's a nonlinear relation to area and defect rate. So the wafer cost and area is fixed, but the defect rate determined by manufacturing process and die area determined by architecture. What it's saying is that because your defects can be all over the place, it turns out that it has a quadratic relationship, and that your defects, adding another defect per wafer, bless you,
Thank you.
increases it quadratically, not just linearly, your yield.
So improve the defects.
Is this
You
related
mean
to the- is this related to like a
decrease the
bell
number
curve?
of defects. Don't
Yeah,
improve
yes.
defects.
Add
You
to
don't
it.
improve.
100% defect. Let's go.
Wow.
Your yield will be 0%.
Yeah. That's an easy thing to calculate.
I mean, you're not wrong.
Well, what if
Actually-
we change this number to what? 0.01?
Whoa. That is good.
It's better.
Should be 0.5 divided. Should be 0.25.
Wait.
Whoa.
No.
No. Stop it.
0.25.
0.25. So it should be 1.25.
You gotta divide
squared.
first. Pandas.
Oh, you have to divide. Who keeps using this division? Who divides? Seriously.
Wait.
There you go. Square it. Wow. There you go.
This one.
This can be better.
1.5625.
So 1 over that is what?
0.64.
So your yield is only 64%, even though you have 0.01.
This is a
Defects.
10% failure?
Uh,
Or 1%? What are you giving your the defect?
Oh no,
rate?
this is your okay, no. Defect per area. Notice that this is for your entire area. Oh, for a single area unit. So what's the chances that you'll have an error inside of a millimeter squared? 1%.
Okay, 1%.
Ooh,
So
that's
our
not bad.
yield is 64% if we have a 1% defect per area.
If we have a 1% chance of a defect within a millimeter squared and our die area is 50 millimeters squared.
Notice the major difference between that and if you had 0% defect. Because that would just give you 1.
Yeah. Yeah, if you had no defects per area, this would all be
Zero.
0, which would make 1 over 1, which would be great. Also, if your die area was 0, it would make this 1 over 1, which again is 100%. All right, now let's change this up just a little more. Let's change it to 5 millimeters.
Oh man.
5 by 2 is not fun.
So it's what, 2.5, so 0.0251. Wow, this is gonna be great. Square that. What's the break now?
This one. 99.9%.
That sounds about right.
Well, your answer
So
in
the smaller
parentheses
the
is
chip.
wrong.
The higher your yield, and the
So the
lower your
answer is
defect
Well,
per
okay,
area,
hold
of
And
course,
it
the
makes
higher.
sense that your cost per die would go down.
Hold
but-
on. We may have done this wrong.
It's 90-something%, I'm pretty sure. Whatever.
I said 95%. I was slightly off. I did the squared
Yeah.
in the wrong spot.
90x%. Good, we're good.
Yeah.
9.
All right. Any questions on the yield formula? No? Good. All right. Whew, let me go ahead and